Welcome. This screencast is going to introduce you to thermochem and relate what we are learning about energy to the states of matter, what we already know about the states of matter. So there are two types of energy. There's kinetic energy and potential energy. So kinetic energy is the energy associated with movement. And so generally speaking, this is usually discussing the speed of particles. And the average speed of particles is actually the temperature of the substance. So really, if we're talking about kinetic energy, we are talking about temperature. And potential energy is the energy of position. So much like if somebody tells you that you have a lot of potential, it usually means that you're capable of doing something, but it doesn't necessarily mean that you are. So potential energy is energy it's generally referred to as stored energy. And this energy is usually associated with the position of particles or with the attraction of particles to one another. The attractions between particles. So how does this relate to the states of matter and what we already know about the states of matter? Well, if we were to draw a picture of a solid, which we've done before, if we were to draw a picture of the particles, you would draw lots of particles and they would be closely packed. They'd be very tightly packed to each other. Okay, so they're tightly packed. And like we talked about at the beginning of the year, there's not much movement, but they're vibrating or shaking, right? So the particles are vibrating. And because they're tightly packed, this makes solids very rigid. But it also means that it's very hard to separate the particles of a solid. Because they're so tightly packed together, it means that they have a very strong attraction to each other. So they are strongly attracted to each other. Or the particles are strongly attracted to each other. And because they're tightly packed or vibrating, that means that we consider a solid to be the lowest energy state of matter. So they're very low energy. A liquid, however, is a little bit higher energy. It's medium energy. And if we were to draw the particles of a liquid, we'd see a little bit more space between them. They're still fairly close to each other, but they can flow past each other. So close to each other, but can flow past each other. And because they can flow past each other, and they can actually move past each other, they're not as strongly attracted to each other. So they have medium forces of attraction. But if you take a glass of water and you pour it, you can tell that the particles still stay together because you have a stream of the liquid. So it means that there is still a significant force of attraction there. And the gases are our highest energy state of matter that we need to know about. There is plasma, but we're not going to go into that. So the gases are considered to be high energy. And if we look at the particles of a gas, in the same size container, we'd have very few particles. And they are, I'm going to actually draw motion lines in here because they are moving very quickly. Okay, so high energy, they're moving very quickly. And all over the place. And because they are moving so fast, there's actually so much space between them that they have very little attraction to each other. So very little attraction, little force of attraction. Attraction between the particles. So what happens then when we have a change of state? Well, just a quick review. A liquid and a gas. We can change from one to the other, and we can change between any of these. So if we have a solid going to liquid, it's going to be an increase in energy, and that is we call melting. And if we have a liquid, and then we can also have a liquid go to a gas, and that is called boiling. It's really weird writing at an angle like this. And then we can also have a solid go directly to a gas, and that's called sublimation. And you see that in dry ice. We saw that at Halloween when we put the dry ice in the sinks and it got all steamy or all cloudy. The other, and all of the ones in red are when we add energy. We can also remove energy from each state of matter. And so if we remove energy from a liquid, we will end up with a solid, and that is called freezing. And if we remove energy from a gas, it can become a liquid, and that's called condensation. And if we remove energy from a gas, it could also become a solid, and that is called deposition. And if we were to take a graph of temperature versus time, if we were to graph the temperature versus time from a solid, and when we were heating it, you might think that it would go like this, where we would have a solid, a liquid, and a gas, but that's actually not what happens, because that doesn't take into account both types of energy. And this is called a heating curve. So what a heating curve actually is it is a graph that shows the change in temperature as energy is added to a substance. So when you look at a curve like this, you can see that there's two distinct parts of the curve. There are inclines, or parts that are sloped, and I'll call that an incline. And there's parts that are flat or horizontal, and I'll call those plateaus. That's not a really good plateau, but you can see it better on the actual graph here. And if we're adding energy the whole time, you see on the inclines you have a change in temperature. But on our plateaus, there's no change in temperature. So if we go back to what we defined our two types of energy as, where a kinetic energy is temperature, then our plateau cannot have a change in kinetic energy. So that if we know that energy is being added, though, that means that it must be a change in potential energy. And on our inclines, because we have this temperature change, that must be a change in kinetic energy. So I'm going to add on here. This little triangle means delta, and so that's the Greek letter capital D, and in math it's used to abbreviate change. So to save myself space, I'm going to go ahead and use that. So that's a change in kinetic energy. On a plateau where there's no temperature change, again, that's a change in potential energy. On this incline, we're going to have another change in kinetic energy. On this plateau, we're going to have another change in potential energy. And you're going to have another change in kinetic energy here because we see a temperature change. Now, some other interesting and unique things that happen that are associated with these inclines and plateaus. If you were to take this substance and you were to watch it as you're heating it and measure the temperature, well, when you start out, you'd start out with a solid. So here we would have a solid. As you add energy, it's eventually going to melt. Once it starts melting, once you start seeing liquid appear, that's when this temperature stops changing. And the reason is because we have that change, that the energy is, instead of being used to speed up the particles, like it's happening in a heating, when it's just a solid, those are being used to, that energy is being used to change the potential energy and actually separate the particles more. So from here to here, that's when it's going from a solid to a liquid, and it's actually melting. So on the lower plateau is when you have melting happening. And then again, you'll see the temperature increase again, and that's when the state of matter is all liquid. And then it's going to stop changing again. And that's what's going to happen is you're going to see the substance boiling. So what's actually happening when the substance is boiling is all of the energy that you're adding is used to completely separate the forces of attraction between those particles and really separate them. And that requires a lot of energy. And then the last part is then it's a gas. And you could continue heating that, and you just see it would continue to increase. So plateaus really signify changes of state. And what's happening to the particles in a heating curve on those changes of state is that the particles are being separated. Or the forces of attraction are getting weaker. And on the incline, what's actually happening with those changes of temperature, remember when we said that it was kinetic energy is the speed of the molecules. So on a heating curve, as you're adding energy, the molecules are speeding up. And there's some other pieces of information that we need to know about when we are talking about, or some other key pieces on our heating curve. So this point right here, point B, when that state of matter starts going from a solid to a liquid, that is called the melting point. And then right here, as soon as it is done going from being when it's completely liquid, when there's no longer any solid, that on a heating curve is actually the freezing point. And then point D here, when the state of the substance stops being a liquid and starts being a gas, then that is called the boiling point. And the point across from that on the plateau, where there's no longer any liquid and it is just a gas, is called the condensation point. Now, some interesting things to note is that the melting point and the freezing point are at the exact same temperature. That means melting and freezing happen at the same temperature. And you'll also see that boiling and condensation also happen at the same temperature, but it's a different temperature than melting and freezing. So if I were to ask you to determine what the melting point of this substance is, and I gave you a graph, the way that you would do that is you would find the lower plateau and you would go over and you would just draw a line. You would just extend this line all the way over to the axis, and right here, right there, is your melting point temperature. And then same thing for the boiling point or condensing point. You would go to the temperature, the second plateau, and you would extend the line over to where it hits the axis here, and you would take that temperature, and this is the boiling temperature. So now I want you to take a minute and try and sketch a cooling curve. And then, so pause the video, sketch what you think a cooling curve is, including the plateaus and the inclines, and also the states of matter. and your boiling point, melting point, freezing point, and condensing point. And then I'll come back and you can check what you got. So to draw a cooling curve, we start exactly the same way. We draw our axis, and because this is my awful, or it's going to be not as pretty as the last one, but in a cooling curve, um, instead of increasing energy like we did with the heating curve, a cooling curve is going to be removing energy. So in this case, you're going to start off with a high temperature, and you're going to start off with the incline. Pretend that that's straight, and then you're going to have a plateau, and then you're going to have another incline, and then you're going to have another plateau, and then you'll have another incline. And so you'll still have your temperature over here, and you'll still have your time here, but like I said, instead of adding energy, you're removing energy. So we start off with the state of matter of this first incline. This first incline, because this is the high temperature, it's the highest temperature, so that means it's going to have the highest amount of energy, and so that means that this one we're starting with a gas, and then the second incline is going to be a liquid, and then the last incline is going to be our solid, or our lowest energy state of matter. So same thing when we go from a gas to a liquid. Instead of boiling this time, this is called condensation. And instead of melting this time, this is freezing. So when something is condensing, you have a state that has both gas and liquid in it, a substance that has both gas and liquid. And when something is freezing, you have a substance that has both liquid and solid in it. So on these plateaus, you actually have two states of matter, and on these inclines, you only have one state of matter. That's an important point that I forgot to make in the last slide. So now we've got those. Now let's add our changes in kinetic energy and changes in potential energy. Same deal as before. Our inclines have changes in kinetic energy, so we start with a change in kinetic energy here, and we'll have another change in kinetic energy here. On every single incline, it's going to be a change in kinetic energy. And then on our plateaus, just like before, it's still a change in potential energy. In this case, though, instead of the energy being used to separate the particles, the energy is being when the energy is removed, the particles move closer to each other and the forces of attraction are getting stronger. And in this case as well, in the kinetic energy, the particles are slowing down. The next thing that we need to add is our points of interest. So we'll add those in blue. So here we have a gas that is just starting to go to a liquid. So right there is our condensing point. And we have on the other side of that condensing point is our boiling point. And then here we have a liquid that is just starting to become a solid. So that is our freezing point. And here we have, on the other side of that plateau, is going to be our melting point. And there I think we have all of the important things labeled that we had before. Again, to find out your boiling temperature or condensing temperature, you would go to your top plateau here and go over, and this would be our boiling temp. or the temperature at which it condenses, either one, because it's the same temperature. And to find our melting or freezing temperature, we would also go to that, we'd still go to that second plateau, and we would go to see where that hits the axis. And we would read that temperature off of that graph. So if you have any questions, please bring them to class.